Hello everyone, welcome back. In previous session, we discussed about the computation of slope and deflection of a simply supported beam. In this session, we will try to compute the slope and deflection of a cantilever beam using conjugate beam method. First, let us take up the problem. Determine the slope and deflection at free end of a cantilever beam supporting UDL throughout the span of the beam using conjugate beam method. This is the cantilever beam. First, let us try to draw a bending moment diagram. This is the bending moment diagram. The value is WL square by 2. This is sagging, so it will be in the negative. So now try to draw the M by EI diagram. What is the M by EI diagram? That is M is WL square by 2 divided by flexural rigidity of the beam. So if I try to draw the M by EI diagram, it will be WL square by 2 EI. This will be my M by EI diagram. So since it is negative, the load will be acting in the upward direction. Now let us try to draw the conjugate beam here. This is M by EI diagram. Now when we convert the real beam into a conjugate beam, as per theory of transformation, free end of the beam will become cantilever and fixed end will become free end. Therefore, point B will become fixed and point A will become free. Now for this conjugate beam, we will transform the loading, that is M by EI diagram. The loading will be in this pattern. The value is WL square by 2 EI. Now we need to find the slope and deflection at the free end. The slope will be here, theta B, and the deflection will be here, delta B. Now we have already drawn a conjugate beam. Now we will try to compute the slope and deflection for this beam. What do you mean by slope? In conjugate beam, slope is defined as the shear force. Therefore, shear force at B, VB is given by area of the parabola Therefore, area of the parabola is 1/3 times of base into height. Base is L, height is WL square by 2 EI. Therefore, shear force at B will be equal to WL cube by 6 EI. As per conjugate beam rules, slope at B will be equal to shear force. Therefore, slope at B will be equal to WL cube by 6 EI. Now let us compute the deflection. As per conjugate beam theorems, maximum deflection will be equal to maximum bending moment We know the value here. It is WL square by 2EI. First, let us take the CG point. The load will be acting here. Let us consider the load as W1, and the CG is placed at a distance of 3L by 4 from the fixed support and L by 4 from the free end. Now maximum deflection at B will be given by maximum bending moment. Therefore, bending moment at B will be equal to W1 into X1. X1 is the distance of CG spaced from the fixed support. Therefore, let us calculate the value of W1. W1 is the area of parabola, that is half into L into WL square by 2EI. It is it is 1 by 3 times WL cube by 6EI, and X is at a distance of 3L by 4. Substituting both the values, WL cube by 6EI and 3L by 4, we get WL raised to 4 by 8 EI. This is the maximum bending moment at point B. Therefore, as per conjugate beam theorem, maximum deflection at point B is equal to maximum bending moment at point B will be equal to WL raised to 4 by 8 EI. Now let us take up the next problem. Determine the slope and deflection at free end of the cantilever beam supporting a point load at the free end using conjugate beam method. This is the beam, which is a cantilever supporting a point load P at the free end. First, let us try to draw the bending moment diagram for this. The bending moment diagram will be a triangular shape in the sagging portion. So bending moment will be P into L. Now we need to draw the M by EI diagram. M is the P into L divided by EI means flexural rigidity of the beam. Therefore, M by EI diagram will be PL by EI of this moment diagram. This is M by EI diagram. Since it is sagging, load will be acting upwards. Now let us try to draw the conjugate beam. As per transformation theory, fixed end in the real beam will be equal to free end of the conjugate beam, and free end of the cantilever beam will be at fixed support. For this conjugate beam, let us load the M by EI diagram. So this will be a conjugate beam loaded with M by EI diagram. Now we need to compute the deflection at the free end. This will be theta B and this will be deflection at B. Here at the fixed end, slope will be equal to 0 and deflection also will be equal to 0. Now according to conjugate beam theorems, maximum deflection will be equal to maximum bending moment and the slope will be equal to shear force. First let us compute the slope. Shear force is equal to theta B. Therefore, VB will be equal to area of triangle is half into base is L and height is PL by 3 EI, PL by EI. Therefore, the value will be PL square by 2 EI. Therefore, theta B will be equal to PL square by 2 EI. Now, let us compute the deflection. So the CG of this triangular portion acts at this point at a distance of 2L by 3 from the fixed support. So this will be our X1 and the load acting at the CG will be W1. As per conjugate beam theorem, maximum deflection is equal to bending moment. Therefore, maximum bending moment at B need to be calculated. It is W1 into X1. Let us compute W1. W1 is half into base is L into height is PL by EI. And X1 is 2L by 3. Substituting the values, we will get PLQ by 3 EI is the maximum bending moment at B. Therefore, maximum deflection delta B will also be equal to PLQ by 3 EI. Now we will take up another problem. Determine the slope and deflection at free end of the cantilever beam as shown in figure below using conjugate beam method. This is the problem. This is a cantilever beam where half of this cantilever beam is loaded with uniformly distributed load of W kilonewton per meter. First, try to draw the bending moment diagram for this. So half of the portion will be parabolic. So the loading will be W into L by 2 and half of this L by 2 will be L by 4. Therefore, W into L by 2 into L by 4, its value will be WL square by 8. This is the bending moment diagram. Now we need to draw the M by EI diagram for the same. So this will be our M by EI diagram. Now let us draw the conjugate beam. As per this transformation rule, free end will become fixed support and fixed support will become free end. For this conjugate beam, let us load the M by EI diagram. WL square by 8 EI L by 2 L by 2. This is A and this is B. So we need to compute this theta B as well as this deflection, maximum deflection at B. Therefore, as per this conjugate beam theorem, slope at B will be equal to shear force at B. First, we will calculate the shear force VB. Shear force VB will be equal to area of M by EI diagram. The area will be 1 by 3 into L by 2 into WL square by 8 EI. On simplification, we will get WL cube by 48 EI. Therefore, slope at B will be equal to WL cube divided by 48 EI. Now let us compute deflection for the same. Half of the span is L by 2. Load is acting at this CG point. CG distance is equal to 3 by 4 times of L by 2. So our x1 will be 3 by 4 times of L by 2 plus L by 2. So we, according to the conjugate beam theorem, maximum deflection is equal to maximum bending moment. Therefore, maximum bending moment at B can be calculated as W1 into X1. Here W1 is equal to 1 by 3 times of height is WL square by 8 EI. Base is L by 2. Height is WL square by 8 EI. On simplification, we will get WL cube by 48 EI. X1 is 3 by 4 times of L by 2 plus L by 2. Therefore, substituting the values here, WL cube by 48 EI into 3 by 4 times of L by 2 plus L by 2. Therefore, maximum bending moment at B works out to be 7W L raised to 4 divided by 384 EI. Therefore, maximum deflection at B will be equal to 7WL raised to 4 divided by 384 EI.